So, Chapter 10, Day 2. T star. Now, some of this is going to clarify a little bit more on the Z star calculation as well as T star. So, margin of error. We mentioned it the other day. The margin of error, M, is just the back half of these calculations, plus or minus Z star times sigma over root n. That is the margin of error. You're taking an x bar value and you're adding and subtracting a little bit to it in the calculation that we learned last time. So what if we have a desired sample size and we don't know the margin of error? So a margin of error, or I should say the other way around. We have a margin of error, but we need to know the sample size. Why am I putting an E on that? I need to go back to kindergarten. For a desired sample size. The calculation for this is going to be Z star times sigma over root n is less than or equal to the M. So let's say we want a particular margin of error and we want to know how big the sample needs to be for that margin to occur. That would be the calculation we would use for that. And we use Z star when we make a confidence interval inference about an unknown mu. Run out of space there. And on top of that, Z star is used when sigma is known or given. I mentioned earlier that I think the situation is highly unlikely that you're not going to know mu when you know sigma in a population. Why would you know the standard deviation without the mean? It just seems like an unlikely situation in the real world. So that's where the next part of our information goes. Standard error. Standard error is used when the standard deviation of a statistic is estimated from the data. this statistic as S, or S sub x, the result is the standard error of the statistic. And that's potentially how you'll see that phrased, as the standard error of the statistic, and that statistic being x bar. So the standard error of x bar is S over the square root of n. So what this really boils down to is, what if we don't know sigma? No big deal. We calculate S and we use it. Okay? This is where we sub for sigma over root n. Now that changes one other thing. That substitution is a t statistic. A couple things you need to know about the t statistic is, or are, it is not normal. What it is a t distribution, which means that it has its own shape, it's just not normal. Which makes our life easy, actually. So when we substitute S for sigma, we also have to substitute T star instead of Z star. And when we need to use T star, we use this table, the T distribution of critical values. Now, the one that I gave you guys is called Table D, but understand that different sources might call it different things. The only one that seems to be consistent is Table A. Everything else can be called something else. So, if we refer to it as Table D, you might look at the wrong table if you're looking at somebody else's information. Yeah, Abby?
So with the standard error, it says that the standard deviation is estimated from the data. When we're not, I guess, evaluating standard error, what is the standard deviation estimated?
Well, if it's sigma, it's not estimated at all. It's actually a parameter from the population, right? So it's, right? Sigma is a parameter from the population. Statistics are when we take the sample and, yeah, make a estimate. Okay, so far so good. Is everybody with me? All right, we're almost done. So we have a new formula for this. It's really not that new. It's a one sample t interval. And it works like this. X bar plus or minus t star instead of z star times the standard error, s over square root of n. Now, in my opinion, this is the thing that you would use a whole lot more often in the real world, simply because we're usually using samples, not population values. We're trying to figure those out. So t star is the critical value. I don't know what makes it critical. Maybe it's on its last legs. I don't know. Okay? It's the critical value of n minus 1. This is the other thing about this that's a little different, but it's super simple. This n minus 1 idea is called degrees of freedom. And I can't help but getting some weird idea in my head about some critical value going into the hospital and the doctor saying, well, we need to set them free, cut off all life support or something. I don't know. Just weird stuff goes through my mind. Sorry. So when we make an inference about mu, maybe it's how I remember this stupid stuff. Right? When we make an inference about a population mean using a t-distribution, the degrees of freedom are I'm just going to use df. Usually that's how it's abbreviated. N minus 1. Let me see if I can kind of explain what the n minus 1 does. Let's say you want a confidence interval that's 99% because you're testing some drug, but you don't know what sigma is, so you've got to use a t-distribution. If you use n, you might actually be calculating something slightly smaller than 99%. So by doing n minus 1, what it does is it ever so slightly expands this capture to make sure that it's at least 99%, if not a little bit more, because you'd rather err on the side of caution, especially with a drug, right, than to make a mistake. So it's error. It's kind of like an error on the side of caution here. It makes it just a little bit wider so that you don't go to court and get sued for a simple mistake, okay, or for something along those lines. Does that make sense? Okay, so we'll gosh, I'm going to use up all the time, and I apologize. We'll do a problem with this, but not all the problems assigned today are using the t-chart. So maybe to give you a little bit more time, I'll skip one that doesn't, and we'll do one that does, since we ran through some problems that did kind of what I wanted to do on the sample problem. So 10.3 830, I think, is the one I wanted to go over. Yeah, vitamin C content. So this problem it starts on page 649, goes on to 650. And it says that in 1996, the U.S. Agency for International Development provided 238,300 metric tons of corn-soy blend, CSB, for development programs and emergency relief in countries throughout the world. CSB is highly nutritious, low-cost, fortified food that is partially pre-cooked and can be incorporated into different food preparations by the recipients. That sounds lovely. I think I'll get some tonight for dinner. Corn-soy blend, yeah, I'm in. A part of the study to evaluate appropriate vitamin C levels in this commodity, measurements were taken of the samples of CSB produced in a factory. The following data are the amounts of the vitamin C measured in milligrams per 100 gram of blend of dry basis for a random sample size of 8 from the production rate. So we have these samples that are 26, 31, 23, 22, 11, 22, 14, and 31. And what we want to do with those, well, no sigma was given. It didn't say anything about it being normal. It does say random sample, so I'm going to just put a note over here, SRS. If it says random sample, we can call that an SRS. I think it is also reasonable to assume that the samples are independent, that they're not taking a sample, testing it, and then taking the corn-soy blend and putting it back in the pot that they're taking other samples from. I think that's reasonable to assume. So I think it's independent. And since we don't know sigma, it's going to be a t-distribution, which is already not normal. So normal is not necessary, but we might still kind of look and see what the data is doing. So take a minute and put those in your calculator if you haven't yet. I have them in my L5, it looks like. Might wait till we get done with this problem. I would, yeah. That way you see how all this stuff works. Okay, so some stuff that we're going to need. We're going to need X bar. We're going to need S. We know what N is. Or we should. It's 8. We've got 8 bits of data. So how do I get these guys out of the calculator? 1 var stats. That'll do it. Yeah. So I'm going to go to stat, calc, 1 var stats. Now my list is in L5. Yours probably isn't in L5, but wherever your list is. The frequency of the list, we never mess with that. And we calculate, and we've got X bar is 22.5. And SX. Now, SX is the standard deviation S. It's about 7.2. It also gives this sigma value. We don't ever use this. Okay? Don't use this guy here. You might go, oh, there's sigma. I can use the Z. No, no. If you've calculated it, go with the S. Okay. So, it says what conditions must be satisfied in order to make an inference about mu, the means of vitamin C, blah, blah. Determine whether each of the conditions is met in this case. So, conditions, it's an SRS, that's given. It's independent. I think that's reasonable to assume. think it's reasonable to assume, and if I was answering this for the AP, I'd probably write something that samples of this corn-soy blend are independent, something like that. How about normal? Generally, we want to look at that. I don't have it by the central limit theorem. It's not given that it's normal. So the only option I really have here is to look at the graph. So what I want to do is I want to graph. I want to do I want to do two graphs really. I want to do a box and whisker on the data. So again, mine's an L5, but yours is probably not. And what I'm looking for is any kind of crazy outliers. So if I graph the box and whisker, it looks like it's a little skewy to the left perhaps, but it doesn't show an outlier. So no outliers, that's good. I'm going to go back and I'm going to graph then the histogram with the same L5. And it's going to give me something weird until I zoom 9 that. Yes, sir.
My calculator says memory is insufficient for the calculation.
That's a problem. Give me a second and I'll see what I can do. I don't know that you need it. You can kind of look on here, all right? So here's where we kind of have to infer a little bit. I've got a graph here that sort of looks like it's approaching kind of some normalcy, right? It does have a gap in here and this one's a little bit low, but keep in mind we only have 8 samples. So is it reasonable to think that if we did have more samples that probably it would kind of be heading in a normal kind of direction? Okay, so I think that by graphing we can say this is very roughly normal. And I'm just going to make a note that we looked at graphs, graph. If I was answering that again for the AP, I'd probably say something like that there's no outliers and that the histogram appears to be heading in a normal direction or something like that. B, is it appropriate to use methods based on the normal distribution to analyze this data? Explain why or why not. And the answer is no, because sigma is unknown. If we don't know sigma, we can't use the table A. So C, find and report the mean, standard deviation, and standard error of the margin of error for a 95% confidence interval. Well, I've got the mean, I've got the standard deviation. The standard error is going to be, we call that SE, is going to be 7.2 divided by root 8. But I'm not going to worry about that right now. I'm actually going to go ahead and do the calculation.
What's the wrong one?
Is that the wrong problem? Where am I reading that from? Oh, sorry. Oh, yeah. Thanks. I hate when that happens. I need a bookmark. Okay, never mind. That's what the standard error is anyway. But so it says calculate the 95% confidence interval. So at 95%, so what I need is I need x bar plus or minus t star times standard deviation over root n. That's what I want to calculate. Now, that requires us to use that new table. Is our critical values table. So one other thing that we need is we need degrees of freedom. So degrees of freedom is going to be n minus 1, right? 8 minus 1. So look at our new table here. It's actually pretty useful. We can either look at the upper tail probability, which means what percent would be in the tail, in either of the tails really. If a 95% confidence interval is what we're looking at, it's going to be 2.5%, right? So 0.025. But if you look at the bottom, I think it's almost even better. Down here it gives the confidence interval. If our confidence level is 95%, all I have to do is find my degrees of freedom on the side, which is 7, find my 95%, and boom, it's 2.365 is the t-star value. So degrees of freedom, n minus 1. Look across the bottom and find your confidence level that you want. We want 95%. There we go. So in a way, I think it's more friendly than the than Table A. Okay, so to finish this up, X bar is 22.5 plus or minus 2.365 times S, which is 7.2, divided by the square root of n, which is 8. And we go to the calculator. See if your calculator has memory for this one. Huh? Or is it just totally stuck?
It's just stuck on all the graph, I think.
Try hitting reset on the back. There's a little button on the back. So I'm going to go 22.5 minus 2.365 parenthesis 7.2 divided by square root of 8. So I get that that's 16.5 about. To change that to a plus 28.5. All right, so here's how we answer this. We say we are. I don't know why it's always we if you're the only one calculating it, but we are 95% confident that the true mean vitamin C content is between 16.5 and 28.5, and I want to go back and figure out what the measurement is there on that. Milligrams per 100 grams, yeah, so mg per 100 grams. There we go. So it's still confidence interval, but the nice thing is about the T is, look at what your choices are on the bottom there for your confidence levels. That goes all the way up to 99.9% confidence level. You can't actually have 100%, but boy, that's about as close as you can get. Down to as low as 50. But if you want something like 85, you're kind of out of luck. You sort of have to go in between these, take some numbers in between. All right.